Right. Good morning. So today we'll see some brief introduction about the digital modulation techniques. Right. Are you able to see this slide?
Yes, ma'am.
Yes. Okay. Thank you. So we start with the block diagram of digital communication. So you all know what is digital communications, right? So the communication system broadly classified into analog and digital, right? So in case of analog, the signal is processed entirely in analog, right? In analog form. Whereas in digital communication, the transmitter as well as the receiver, in both the sides, you are going to have the components which can process only the digital input, right? So we need to apply the input should be in the digital form. So what is the advantage of digital communication than your analog communication, right? So in digital, we can process these symbols, we can process only the binary symbols, right? So we can easily transmit, we can easily store those data, as well as we can transmit with less amount of noise or the interference, right? So the communication is also will going to give some high data rate, right? So that is why we go for this digital communication, then highly secured also, right? So we can include the security in the data also. We can compress the data as well as we can decompress at the receiver side, right? So there are so many advantages in digital communication. That's why we go for digital communication instead of analog signal, right? So but the case in physically we have only the analog input, right? So all the inputs which are available is going to be analog, right? So for example, my voice signal, right? So now I am talking, now my speech is going to be an analog signal, right? So I cannot directly transmit this voice signal to further distance, right? So if I going for a long distance communication, I cannot go with an analog signal, right? So if I go for a long distance communication, I need to do with analog modulation. So instead, I'm going to convert this analog speech signal into a digital one, right? So where I'm going to discretize all the amplitude as well as the time period, right? So that is what purely digital signal. So discrete signal is going to be partly analog signal, right? Because discrete is going to be discrete is not a purely digital signal, right? So digital in the case both amplitude as well as the time period should be in discretized, right? That is what the purely digital signal, right? So here the source can produce either analog signal or it's going to be a digital signal, right? So if it is in analog form, so the source can be a human, or it can be a telephone line, or it can be a computer, right? So if it is a computer, it can generate the data in the form of digital one, right? So zeros and ones, right? So no need for further conversion. Whereas if it is an analog signal, we need to convert this analog into a digital form, right? So for that, we need an analog to digital converter before applying to the source encoder. So that is what that's we start with the source, right? So the remaining blocks which are available in the transmitter side will process only the digital signal. So before applying the signal to the source encoder, we need to convert this analog input into a digital one, right? So the first part, I think you might have studied PCM. So PCM is a basic digital communication, right? Digital signal, right? So where we need the input is the PCM is going to have only 3 blocks, right? So sampler, quantizer, and then encoder. So that is what the output is going to be, the digital signal or the binary data, right? So the PCM signal is going to be the pure digital one. So the very basic digital signal is going to be the PCM one, which was initially used in a telephone communication, right? So its data rate is 64 kbps, 64 kbps per second, 64 kilobytes per second, right? So the digital, we need to convert this analog is converted into a digital one. Then it is going to be given to a source encoder. Source encoder will do some it's going to perform including this sampling, compounding, and encrypting. So encrypting is for providing the security to the data, right? So if I need to secure my data, I go with the encryption at the transmitter side and decryption at the receiver side, right? So the basic function of the source encoder is it has to reduce the number of bits in the original message. That is what compression. So for example, if you are going to write a digital video, right? So digital video in compact CD, you need to convert. You'll be doing some compression, right? So zip file, right? So you'll be doing compression, and then it's going to be stored in the CD, right? So that is what a source encoder. So it is going to compress the maximum. So it's going to compress the redundant information in the original message, right? That is what source encoding. So we have different source encoding techniques in the digital system, right? Then the next part is channel encoder. The channel encoder is mainly to overcome the channel noise when we are transmitting this signal over the channel, right? So basically the channel can be either wired channel or it can be a wireless channel, right? In the case of wireless, the signal will suffer with the interference, right? So the signal will basically suffer with the interference as well as AWGN noise. So the noise is going to be additive white Gaussian noise, right? So to overcome this channel noise, so we are going to transmit our signal over the channel, right? So at the receiver side, I need to get back my original signal even though it is affected by the channel noise, right? So I need to do some extra additional information or extra bits which are used to detect whether there is an error in the received signal or not, if it is transmitted over the channel, right? So that part is taken care by this channel encoder, right? So here you are reducing the redundant bits, whereas here I'm going to add some more additional information. So those informations are necessary, that is used to detect whether the received signal is corrupted by the noise or not, right? If it is corrupted, then I'll be detecting some error at the receiver side. So that can be removed. That can be removed by the additional information which I am sending along with the original information. So that is what the function of channel encoder. So here I'll be adding some extra information to the to my original bit, right? So my original data, right? So for example, CRC, cyclic redundancy section, that you'll be using in the network computer network, right? So CRC, so we have studied so many encoding techniques. So convolutional technique is basically used in mobile communication. So you'll be using convolutional encoding technique in the mobile communication. Then we have a RS coding. So this RS coding is basically used for your CD drive, right? So recording of your video. Then coming to the modulator. So if I'm going to transmit over a long distance, I do modulations. I need a modulation. So here you are going to do some digital modulation technique. This block only are going to discuss in detail, right? So that is what modulation. So if I'm performing modulation at the transmitter side, I need the demodulation at the receiver side. So the first block at the receiver is going to be a demodulator, right? Then remaining blocks which is going to perform the function which are performed on the transmitter side is going to be reversed at the receiver side, right? So I need a channel decoder and channel source decoder at the receiver side. So finally I'll get back my original analog or digital signal at the receiver side. So this is what the basic digital communication, right? So we start with the modulation technique, right? So what are the types of modulation? Digital modulation, right? So what is digital modulation? Just you can see the input is going to be a waveform, right? So this is what a line code, right? Either it can be NRZ. So here it is going to be NRZ. So it can be a computer data or it can be a telephone signal. It's converted into a binary sequence, right? The binary sequence are represented in the form of line coding. So the line coding is, you would have studied this line coding NRZ, non-return to zero, unipolar, polar, NRZ, and there are so many different methods of bipolar. The different methods are there, right? So you can use, depending upon the modulation technique, you can go with any of the line coding technique, right? So the input should be represented in terms of, this is the binary sequence. So the binary sequence should be represented, it should be represented in terms of any line coding technique, right? So now this is the unipolar, right? So this is unipolar NRZ, right? And then output should be, just see the output, the output is going to be an analog one, right? So this is what the digital modulation. So I said the broad modulation technique is, broad classification of modulation is digital modulation and analog modulation. In analog communications, in analog modulation, you need a message and you need a carrier. So for modulation, we need a carrier, right? So original information is message and that is going to be carried over by your carrier signal, right? So analog, we have a carrier and we need a message, right? So both the carrier as well as the message is going to be analog form. So carrier as well as the original message both are analog. So I think my handwriting is not legible, right? So both are analog, right? So both are in analog waveform, right? So this is both analog. Whereas in digital, you can see the input is purely digital, right? So here the digital waveform, in the digital modulation, in digital, here the carrier is purely analog. Carrier is a sine wave, cosine wave, right? So it is analog waveform. Carrier is analog, whereas the input is, your message is going to be a digital one, right? So that is what the digital modulation, right? So in between we have one more modulation that is called the pulse modulation. There your carrier is going to be pulse wave, right? So you would have studied this PAM, pulse amplitude modulation, pulse position modulation, pulse width modulation. There are different modulation that is called a pulse modulation, right? Where the carrier is going to be a rectangular pulse, right? So whereas in digital modulation, your carrier is purely analog, whereas your message is going to be purely digital. So now this is the message. It is purely in digital form, whereas the carrier is going to be analog. So the output will be, modulated output will be the analog one. So this analog waveform is transmitted over the channel. And coming to the types of digital modulation. So we have basic classification. So the broadly it is classified into ASK, FSK and PSK. Amplitude shift keying, phase shift keying, and frequency shift keying. This is similar to your analog modulation, right? So in analog you'll be called it as AM, FM and then PM, right? Pulse modulation, right? So here it is called as shift keying. So why we call it a shift keying technique? Because here you are going to keying the input, right? That is zeros and ones are keyed into the analog waveform. So that is why this is called as shift keying technique, right? You are going to shifting the carrier depending upon the binary 0 and binary 1, right? So the amplitude shift keying, frequency shift keying and phase shift keying. Then we have one special modulation technique called as QAM, which combines amplitude as well as the phase shift key methods. So what is amplitude shift keying? So the carrier is turned on and off, which represent binary values. So for binary 0, I'll be switch off my carrier. I'll be switching off the carrier, so which represent the binary 0. Then for binary 1, I'll be switch on my carrier, right? So the carrier is switched on and off to represent the binary values. That is what ASK. And FSK is switching between two different frequencies. So I'll be choosing two frequencies for carrier. So I said the carrier is going to be a analog waveform. So I can choose two different carrier frequencies, F1 and F2, right? So F1 can be for binary 0 and F2 can be for binary 1. So that is what frequency shift keying. And then phase shift keying, I'll be choosing two different phases to represent binary 0 and 1. So here the data is going to have only two values, either binary 0 or binary 1. So I can choose only two phases for representing binary 0 and binary 1. So that is what PSK. Then QAM. So QAM is a combination of both ASK and FSK. So let's see the amplitude shift keying. You can see the amplitude shift keying. So already I told you this modulation technique, the digital data has a variations in the amplitude of the carrier wave, right? So this amplitude represent the binary data. So here mainly the information is carried in the amplitude of your ASK waveform, right? You can see the example here. Chosen two different amplitude. Either you can go with an on-off method or you can go with two different amplitude also, right? So here the lower amplitude representing, you can see the lower amplitude representing binary 0, whereas this higher amplitude representing binary 1, right? So just see this bitrate and baud rate. Here you are given with the bitrate is equal to baud rate. Bitrate is equal to 5. Baud rate is equal to 5. So we should know what is bitrate and what is baud rate, right? So finally, I'll tell you what is the difference between bitrate and baud rate. Now just see this bitrate. What is bitrate and baud rate for each and every modulation technique, right? So here the bitrate is 5. So why the bitrate is 5? I am transmitting 5 bits in 1 second. You can see 5 bits in 1 second, right? So I'm transmitting 5 bits per second, right? So that is what bitrate, right? The baud rate is also 5. Every baud I'm transmitting 1 bit. So the baud rate is also equal to 5, right? So for ASK, bitrate is equal to baud rate. This is also an important concept, right? So what is the bitrate and baud rate for amplitude? ASK, both are equal. So this is what on-off keying, right? So your S of t is represented by S of t is ASK modulated waveform. ASK modulated waveform. So this ASK modulated waveform is represented S of t is equal to A cos 2 pi FCT. So this representing an analog waveform A into cos omega ct, right? So that will represent the analog waveform, isn't it, right? So A representing some amplitude of the carrier, and cosine wave is the carrier with some frequency fc, right? So binary representing binary 1, whereas I'm going to switch off the carrier for representing binary 0, right? So this type of modulation is also called as on-off keying, or shortly this is called as OOK signaling. OOK signaling, it's going to be on-off signaling, right? So on-off keying, OOK is nothing but ASK modulation, right? So just see the example. The baseband PCM signal is represented in unipolar forms. One is represented with some amplitude and 0 is represented with 0 amplitude. So this is an unipolar form. Now you can see the amplitude shift keying. The carrier is switched on only for this one, right? So binary 1, right? So till this period, each bit is represented with some bit duration, right? That is what TB second, right? So the TB is going to be constant for each and every bit, right? So for every bit duration, if it is going to be 1, I'll be switching on the carrier. Then for 0, I'll be switch off my carrier, right? So this is the off state of my carrier. This is the off state, right? Off state of the carrier. So this is what the this is what the amplitude modulation. Right. So how can we generate this ASK? How can we generate this ASK? We need a simple modulator, simple product modulator. So for OOK signaling, I'm going to multiply 0 and 1. So the binary value is either 0. Binary is going to be either 0 or 1. I need a cosine wave, right? This is going to have some amplitude, right? A carrier. So this is the carrier. So the carrier is going to be simply multiplied by the input binary symbol, right? So if the input is going to be 1, it is multiplied by cosine wave. The output will be the cosine wave, right? If the input is 0, the output will remain as 0, right? So I can produce this ASK analog amplitude shift keying signal simply by multiplying the carrier along with the binary. So either the carrier will be the output or the 0 is going to be the output, right? So this is what the simple ASK modulator. So the signal space diagram for ASK. So for simple binary, M is equal to 2. Simple binary case, if it is a only binary 0 and 1, only one bit is transmitted, then it is going to be M is equal to 0. This is what the binary case, binary ASK. So we need only a single base function, right? Basis function that you would have studied in digital communication, right? Single basis function. So it is a one-dimensional signal. ASK is one-dimensional signal, and PSK is also one-dimensional signal, right? Then M is equal to 2. If M is equal to 2, there are 4 combination, 2 power 2. There is a MRA signal, so 2 power 2. So I'll be grouping 2 symbols. So this is also, I can represent with 4 different amplitudes, right? Similarly, M is equal to 8. So this is a signal space diagram, or it is called as Constellation Diagram of ASK. Then what are the disadvantages of ASK? So ASK again similar to your amplitude modulation. The disadvantages of amplitude modulation is same for your ASK also. Here also the information is carried by the amplitude. So the information can be affected by the noise, right? So most of the time it is not used in the digital communication. Bandpass communication we doesn't use this ASK at all, right? So we go with FSK or PSK. But this is the basic one. So coming to the FSK, we are going to use two different frequency. You can see 0 is represented with low frequency and 1 is represented with high frequency. Here also the bit rate is equal to baud rate, right? So number of bit transmitted per second is equal to bit rate, right? And baud rate is also equal to the same, right? So here I'll be using two different frequency, high frequency for binary 0 or 1 and low frequency for binary 1 or 0. So this can be represented as S of t is equal to a cos 2 pi f1 of t and a cos 2 pi f2 of t is representing binary 0. I can choose any frequencies, right? High frequency to 1 or low frequency to 0, right? I can choose high frequency or low frequency to represent two different binary, right? So here I need a simple modulator, right? But here I need two carrier, right? So just see here, this is converted into a polar NRZ. So one is multiplied by F1, right? So one is multiplied by the carrier with the frequency F1 and minus 1. The polar in polar will be representing 0 as minus 1, right? So the amplitude should be inverted to get the positive value, so that this will be multiplied by F2, right? So the carrier, second carrier, the output will be added to get the FSK waveform. Then PSK, I'll be choosing two different phase angle, right? So one is represented by 0 phase and 0 is represented by 180 degree out of phase, right? So you can see this is a 0, this is 0, but here it has chosen as 180 degree phase shift for 0 and no phase shift for 1. I can choose anything, right? So either I can go with S of t is equal to a cos 2 pi fct without any phase shift. I am representing binary 1. By shifting the carrier 180 degree, I can represent binary 0. So this is on, again this is going to be a change in the amplitude. So here it is represented by positive carrier and this is going to be the negative carrier. So cos 180 plus theta minus cos theta, right? So this will become a negative carrier. So I have to invert the carrier, that's all, right? So 1 is represented by without any phase shift, whereas the 0. So see the 0 will start with the 180 degree phase shift, right? I am just inverting amplitude. Just see the amplitude. Now this is the positive amplitude and this is going to be the negative amplitude. So I am just shifting the carrier to represent the binary 0. Then this is the constellation diagram for only the binary PSK. So binary PSK, I have only 0 and 1. So bit is going to be 0 and 1. So I need only single basis function. Again, this is going to be a one-dimensional signal. So 0 and 180 degree, right? And this is 4 PSK. I can combine two bits. Then I'll be choosing the phase difference as 90 degree, right? So each message point is shifted by 90 degree out of phase instead of 180 degree. So the 360 degree is divided by 4 now, right? So this is called Diabet transmission. So whenever I'm combining two bits together, it is called Diabet transmission. If I'm combining 3 bits, it's going to be Tribit transmission. So this is Tribit 8 PSK, then it's going to be 45 degree out of phase. Right, so modulator, again this is, I said this is similar to your ASK modulator because here also you are going to represent the message binary 0 and 1 in the form of amplitude. One is the positive amplitude and another one is going to be negative amplitude. So I can directly apply this polar NRZ to a product modulator with the carrier, right? So one is directly multiplied by this cos omega ct. So I'll be getting the positive cosine wave, right? Whereas if I'm multiplying with minus 1, 0 is represented by minus 1 in polar form, right? In polar form. So this is going to be minus 1. When I'm multiplying with carrier with negative value, I'll be getting negative carrier, right? So the modulator is very, very simple for PSK also, right? And decoder, at the demodulator side, I need a correlator. This is what a receiving filter, right? Correlator, the correlator filter will produce some points, right? This is going to be the signal point, right? Decision point. From this sampling point, I'll be taking the decision on the binary 0 or 1. So I have to choose some threshold value. Decision device is always given with some threshold value. Mostly this is going to be 0, right? Because I'm going to check whether it is greater than 0 or less than 0. If it is greater than 0, then the transmitted symbol is going to be 1. If it is less than 0, now this indicates a negative amplitude, right? So it is obviously it is going to be binary 0. Binary 0, right? This is simple modulator and demodulator for PSK. Now coming to the bitrate and baud rate. So what is the difference between bitrate and baud rate? So the bitrate is defined as number of bits transmitted per second, whereas baud rate is number of signal transmitted per second, right? So that is the difference between bitrate and baud rate, right? So most of the time the bitrate is always less than or equal to the bitrate, right? So baud rate is always less than or equal to the bitrate. Where you'll be using the bitrate means you'll be using for data communication. So the bitrate is used in measure the computer efficiency. So you'll be call it as kbps. Everything in the data communication, the computer network will be call it as bits per second, right? So now kilobits per second, megabits per second, right? So the computer efficiency measured in terms of bit rate, whereas the data transmission will be called as baud rate, right? So how many number of signals are transmitted? So the signals means you are going to transmit the waveform. The waveform should carry the information, binary zeros and ones, right? So I'll show you the difference in the next slide, right? So I'll show you how this baud rate and bit rate are different for in other modulation technique, right? So we have different digital modulation technique. In those techniques, there is some difference between bitrate and baud rate, right? So till now we discussed ASK, FSK, and PSK. In all the three cases, the bitrate is equal to baud rate because every baud you are going to transmit 1 bit. Similarly, in every bit you are going to transmit only 1 bit, right? So 1 second, right? So this is going to be the same. Just take the formula for baud rate. So the baud rate is equal to bit rate by number of bits per signal unit. So the number of bits per signal unit is number of signal transmitted, right? So the formula is bit rate divided by log base to m. This m represent the array signaling, right? Number of symbols transmitted. This is what the m array, right? So if m is equal to 2, that represents the binary transmission. Let's take this problem or take down this problem. The bit rate of signal is 3600. If each signal unit has 6 bits, what is baud rate? What is baud rate? What is baud rate? What is baud rate? So first you write the formula. Baud rate is equal to bit rate by number of bits per signal unit. So bit rate is given as 3600. So 3600 divided by number of bits transmitted is 6. So every signal you are transmitting 6 bits, right? So divided by 6. Put divided by 6. So the baud rate is 600 bauds per second, right? So the bit rate is represented in terms of bits per second, whereas the baud rate is represented by bauds per second. Bauds per second. Right. So have you completed this problem? You just take this formula and then this solution also. We'll move on to the next one. So coming to QAM. So I said this QAM is the combination of amplitude shift keying and phase shift keying. So here why we go for this QAM is we can transmit a bit, dibit or tri-bit, or we can combine the quadruple bit also, right? So any number of bits can be combined and transmitted with two different phases, that is two different carrier. So here the data symbols are represented by in-phase component and quadrature phase component. In-phase component is cos 2 pi fct and quadrature phase component is sin 2 pi fct. Since the carrier itself is going to be independent, so we can easily demodulate at the receiver side without any interference in the signal, right? So that is why we go for quadrature amplitude modulation. So you can see here we have combined 3 bits, right? Here you can see the bit rate is different than your baud rate, right? So the bit rate is 24, whereas the baud rate is 8, right? Now we can see the difference. What is the bit rate and baud rate, right? So in each baud I am transmitting 3 bits. So the total number of bits transmitted per second is number of bits per bit rate, right? So total number of bits transmitted per second is bit rate, right? So here I have 8 baud, right? So 8 into 3, 24. So I'm transmitting 24 bits per second. So the bit rate is 24. But how many signals I am transmitting? Signals means waveform. How many waveforms I am transmitting? Just see, this is one waveform, S1. This is another waveform, S2. So each waveform is carrying 3 bits, right? But the total number of waveforms to represent the total number of waveform to represent the 24 bit is only 8, right? So the bit rate is the number of waveforms to represent the entire bit, whereas baud rate, whereas the bit rate is number of bits transmitted per second, right? So here each waveform carrying 3 bits. So the 3 into 8, 24 is the bit rate, whereas each signal is going to carry 3 bits. Total number of bits are 24. So I combine 3 bits as the signal, right? So each signal is carrying 3 bits. So totally I need only 8 waveforms to represent 24 bits. So that is the difference between bit rate and baud rate. So now you would have understand why we go for this QAM signal instead of this PSK or ASK or FSK. In PSK and FSK, I need a single waveform to carry the single binary 0 or 1. Whereas here I can group any number of bits which can carried over by a single waveform, right? So that is what the difference, right? Then constellation diagram for 4 QAM and 8 QAM. So you can see here I have chosen the amplitude. This is the single amplitude and 4 different phases, right? So it's going to have a single amplitude. Suppose if it is 2, the 2 is going to be the amplitude, right? Amplitude for all the message points, but the phase angle between all the waveforms, all the message point is different, right? So I am choosing 4 different phases and single amplitude, whereas here it is 8 QAM. So 8 QAM I have chosen 2 different amplitudes. So this is 2 and this may be the 4, right? So the outer square is representing remaining 4 message points, right? So 4 message points using 2 as the amplitude and remaining 4 message points is represented with 4 as an amplitude. Then this is the constellation of 16 QAM. So we can choose a different amplitude and different phases to represent the 16 QAM constellation. So all the 3 represent the 16 QAM, but it has chosen 3 amplitudes, 4 different amplitudes and 2 different amplitudes with different phase angles. So we'll finish off this and we'll move on to the problems. I think what is the time now? Right. So that is the advantage of QAM. So then coming to Qpsk. So Qpsk is a special case of QAM, right? So here we are going to, why we go for QAM means it's going to conserve the transmission bandwidth, right? The half the bit is transmitted over the cosine wave and half the bit is going to be carried over by the sine wave, right? So here you will be transmitting die-bits. This is die-bit transmission. So half the bit is transmitted over the cosine wave and half the bit is transmitted over the sine wave. So again, the transmission bandwidth is going to be reduced, right? So the required is reduced. So the detection is also very simple. So it is widely used in cellular telephones. So this is what the same. So I just rushed up this remaining slides. You can see the amplitude for here. I just combined two bits, right? 0, 1, 1, 0 and 1, 1 and 0, 0. So these are the 2 power 2, right? So only 4 combinations. So Diabet transmissions. Qpsk is a Diabet transmission. So I'll be choosing 4 different phase angles, right? So each phase difference is pi by 4, right? So the signal is represented by Si of t is equal to square root of 2e by t cos 2 pi fct plus this 2i minus 1. So here I varies from 4 message points. So I varies from 1, 2, 3, 4, right? So each message point is different. Each message point is pi by 4 phase angle apart, right? So it is pi by 4. It is multiplied by 5 pi by 4. So this is the signal space diagram for Qpsk, right? 4 message points, and then this is the modulated waveform and Qpsk transmitter, right? I think you would have studied these things in detail, right? So A1 and A2 representing, this is the odd number of bits, and this is going to be even bits. So odd and even bits are demultiplied. That is why here we are choosing we are using a demultiplexer which demultiplies the odd bits and even bits. So this is going to be odd bits and this is going to be even bits. So odd bits are multiplied by the cosine wave and even bits are multiplied by the sine wave, right? So there won't be any interference between between these two waveforms, right? So it's a simple Qpsk detector. Since I am transmitting 2 different carrier, here I needed 2 detector, right? So 2 detector, you can see 2 receiving filter, right? So 2 decision devices, and finally I need to combine this, right? So but because I need to receive 2 bits, right? So I need 2 arms at the receiver side. So disadvantage of this Qpsk, the main drawback of this Qpsk is spectral regrowth. The spectral regrowth is the major drawback of this Qpsk, right? So most of the electronic devices is going to have some electronic noise, right? So the noise, non-linear noise. So those nonlinear noise will amplify this amplitude modulation into this phase modulation. So that is why here the spectral regrowth will happen, right? So that is the main drawback of Qpsk. So that is why we go for OQPSK. And OQPSK, you'll be transmitting signal. OQPSK is offset QPSK. Why offset QPSK or staggered QPSK? Mostly this OQPSK is used in satellite communication, right? So the offset QPSK, why it is called as offset QPSK? Suppose if I am transmitting the 2 symbols, so I said odd and even bits. So odd and even bits are transmitted at the same time duration, right? So if this is going to be the odd bit and this is going to be start at the even bit, right? Whereas in the case of OQPSK, I'll be transmitting the second waveform sometime later than the previous one, right? So that there won't be any modulation. There won't be any 180 degree or 90 degree phase, 90 degree cross, right? There is no phase transition at 0 degree and 90 degree, right? So this you would have studied in wireless communication, right? Wireless communication, let us seen this, right? So why it is crossing the amplitude 90 degree, it directly goes to a 0 amplitude level, right? So instead of the amplitude, suddenly it goes to 0 degree or 180 degree, right? That is what 90 degree or 180 degree phase shift, right? That is the advantage of Qpsk. Instead of we go for offset instead of the Qpsk, right? Advantage of OQPSK. So this is the modulator. So you can see the modulator, we have we are delaying this second waveform, right? So the odd bit is transmitted, odd bit is similarly modulated by your Qpsk, whereas the even bit is delayed by some amount of time ts, right? And it is modulated with a cosine wave, right? So that is the difference between Qpsk and OQPSK. Then coming to the detection, we have 2 different methods, coherent and non-coherent detection. So coherent, we we need a carrier should be in phase with the received carrier, right? So the transmitted carrier should be in phase with the received carrier. So I need a carrier synchronization at the receiver side. Whereas non-coherent detection, I doesn't need any reference phase reference at the receiver side, right? But the thing is here the receiver design is very simple. The coherent detection, the receiver detection is very simple. Receiver's design is very simple, whereas in non-coherent, because I doesn't have any reference for the decoding, it's going to be a complex one. So the receiver design is somewhat complex, right? But most of the communication takes place in wireless communication, so I cannot keep the coherent always, right? So I cannot keep the transmitter and the receiver always in the coherent. Coherent means synchronized, so I cannot keep the transmitter and the receiver to be synchronized all the time. So I go for non-coherent detection, even though the receiver design is going to be complex than the coherent detector. Then pi by 4 Qpsk, this you would have studied. It's similar. It is what differentially encoded Psk, right? So Dpsk, right? So Dpsk is a non-coherent detection of Psk waveform, right? So here you'll be before modulating in Psk, you'll be differentially encoding this input signal, and then it is going to be modulated using Psk. So finally we come to the end. Then we have a minimum shift keying, right? Minimum phase shift keying is another variant of VEC, right? Another variant of VEC. Here it is producing constant envelope signal. Then we have Gmsk. Gmsk is a continuous phase FSK. So this is what continuous phase is, FSK. So most of the communication takes place, most of the mobile communication takes place in Gmsk. So it's reducing the side lobe energy, and then channel spacing is be little bit tighter than the Gmsk. We'll start this problem, right? So take down this. This is going to be the 1 mark, right? Then we'll move on to the 2 mark, right? So in binary data transmission, Dpsk is preferred to Psk. So you no need to work it out, right? So this is very simple question. In binary data transmission, Dpsk is preferred to Psk. Why? Why we are choosing this Dpsk than Psk? A coherent carrier is not required. The first option, a coherent carrier is not required to be generated at the receiver. Then B is for a given energy per bit, the probability of error is less. The 180-degree phase shift of the carrier are unimportant. More protection is provided against impulse noise, right? Can anyone tell me what may be the answer for this question? Can anyone? So just now we completed this, right? Can anyone tell me what may be the answer for this one? Yes, Abhishek. Abhishek.
Yes, ma'am.
Yes, ma'am. You know the answer?
No, ma'am. PSK-னா 180-degree phase shift யூஸ் பண்ணுவோம் மேம். அப்போ நம்ம DPSK போறதுக்கு காரணம் அது இல்லாம இருக்கலாம். தெரியல மேம்.
Just now I told, right? So just see the previous slide. The Dpsk, why we go for Dpsk? So this is what Dpsk, right? So the coherent detection, this is what non-coherent detection, non-coherent. So I said there are two kind of detections, right? Coherent and non-coherent. Your Psk is coherent detection, right? So coherent detection we can use with a we can use with a short distance communication, whereas for non-coherent detection I can go for long distance communication where I cannot keep the transmitter and the receiver synchronized, right? I doesn't need. So for example, your mobile communication, you doesn't require synchronized, right? You doesn't need a synchronization between the transmitter and the receiver, right? Your transmitter mobile can be anywhere, your receiver mobile can be anywhere in the country, right? So anywhere in the world, right? So even you can able to receive the message, right? Is receive the message, right? So we doesn't require any coherent, right? So coherent means phase synchronization is doesn't require, right? In such cases we can go for Dpsk. So Dpsk is one of the non-coherent detection, non-coherent modulation. So we can detect this Bpsk non-coherently. That is why we go for Bpsk. So now can you tell me what is the answer for this? Vedavyas, Vedavyas, Vedavyas. So the answer for this first question is the first one, option A. Coherent carrier is not required to be generated at the receiver. So non-coherent, right? Carrier is not required. So coming to the second question, quadrature multiplexing is quadrature multiplexing. Quadrature multiplexing, it's a QAM signal. So QAM is not same as FDM and not same as TDM and not the combination of FDM and TDM. It is different from FDM and TDM. So QAM is different from FDM and TDM. So that is the answer for the second question. Then for third question, third question, Bpsk system modulates at the rate of Bpsk is a binary phase shift keying which modulates at the rate of. So how many bits per symbol are transmitted in Bpsk? So Bpsk is transmitting only 1 bit. So 1 bit per symbol. It's transmitting only 1 bit per symbol. That is why the bitrate is equal to baud rate for Bpsk. Then coming to the fourth question, in binary phase shift keying, again Bpsk, the binary symbol 1 and 0 are represented by carrier with the phase shift of. So in Psk, what is the phase shift? What is the phase shift to represent 1 and 0? What is the phase shift?
Pi.
It is pi. It's very correct. So it's pi. So the option is option B. 180 degree out of phase. Then coming to the fifth question, in on-off keying. So what is on-off keying? What is on-off keying? On-off keying, the carrier signal is transmitted with signal value 1 and 0 indicates. On-off keying is what kind of modulation? Amplitude modulation. Yes, ASK is very correct. It's an amplitude of modulating signal. So this on-off representing ASK. So binary 1 and 0 is represented by the amplitude. So amplitude of the modulating signal is correct. So it is option C. Then coming to the sixth question, the data rate of Qpsk is dash of the Bpsk. Data rate. So Bpsk, how many bits we are transmitting? Then how many bits we are transmitting for Qpsk? Bpsk, the previous question, we got the answer for Bpsk, right? So how many bits per second is transmit? How many bits per second for Bpsk? It is 1 bit per second, right? Whereas in Qpsk, you are transmitting 2 bits. It's a Diabet transmission. You are transmitting 2 bits at 2 bits per second. So the data rate is twice, right? So twice that of your Bpsk. Here you are transmitting 1 bit per second, whereas Qpsk you are transmitting 2 bits per second, right? So the data rate is twice that of your Bpsk. So the option is C. Option is C. Then seventh question, it's a problem. The bit rate of the digital communication system is given as R kilobits per second. It's R kilobits per second. The modulation used is 32 QAM. So that is an MRI signal. So 32 QAM. The minimum bandwidth required for intersymbol interference free transmission, ISI free transmission. So we need to calculate the bandwidth requirement, minimum bandwidth requirement for ISI free transmission, right? So for bandwidth, W is equal to always RB by 2. So RB is the bit rate, right? RB is bit rate. Half of the bit rate we need required for the bandwidth, right? So W is always equal to RB by 2. So we need to calculate this RB bit rate. We need to calculate for this 32 QAM. So the QAM is given as 32, right? It's a 32 represents the MRI signaling, right? So it's the MRI signaling. So it is equal to log base to M. It is equal to log base to m. So we need to find out so the value of m, right? So this is equal to, you just see the next slide, given the solution also, right? So W is equal to RB by 2. So W represent the bit rate required for the transmission. So RB is equal to half the bit rate. W is equal to RB by 2 is the half the bit rate. So given that it's a 32 QAM, so we need to find 2 power n, right? So 2 power n is equal to, it's given as 32. This is what m. So capital M is equal to 2 power n. It is equal to 32. So n is going to be 5 bits, right? So I can write this RB is equal to the number of bits. Here it is given as RB. It is R kilobits per second, right? So R divided by 5 kilobits per second. We are transmitting 5 bits, right? So R by 5 kilobits per second. RB by kilobits per second. So this is what my RB. So just substitute this RB here. You'll be getting the transmission bandwidth W. So W is equal to R divided by, so instead of this RB, you just substitute R by 5. So here I have 2. So R divided by 10 is equal to R by 10. R by 10 kilohertz. So R is given in terms of kilo, right? So it's a bandwidth. So I should represent in terms of kilohertz, right? So the unit for bandwidth is hertz, right? So kilohertz. So the option is, so the answer for this question is option B. You can see the answer for this question is option B, R by 10. So this is the correct answer, R by 10. Just note on this solution. We'll move on to the next question. Shall we go to next question?
Yes, ma'am.
Yes. So the next question, for a bit rate of 8 kilobits per second, the best possible value of the transmitted frequency in a coherent binary FSK systems are 16 kilohertz and 20 kilohertz. So you are asked to find the transmitted frequency. The bit rate of the signal is 8 kbps. So it is 8 kilobits per second, right? So you are asked to find the frequencies. The frequency is given as 16 kilohertz and 20 kilohertz. Why it's given as two frequencies? Because it's going to be FSK. So for FSK, I need to represent the binary 0 and 1 by two different frequencies, right? So you are given with the two frequencies, 16 kilohertz and 20 kilohertz, 20 kilohertz and 32 kilohertz, 20 kilohertz and 40 kilohertz, 32 kilohertz and 40 kilohertz. Here, there is no much calculation here because it's a simple one. It's given as 8 kilobits per second. So the frequency should be the multiples of 8. So both the frequencies for binary 1, I'll be choosing F1. For representing binary 0, I'll be choosing F2. Two different frequencies, right? So you are given with two different frequencies, but both the frequencies should be the multiple of this 8. Should be the multiples of this 8. You just tell me which combination of frequency is giving this multiples of 8. It should be the multiple of 8. So first option is 16 kilohertz and 20. So 16 is multiple of 8, but 20 is not the multiple of 8. Yeah, it's not the multiples of 8. Whereas option B, 32 is multiples of 8. 32 is multiples of 8, but 20 is not the multiple of 8. So option B is also not correct. Option C, 20 and 40. 40 is coming under the multiples of 8, but 20 is not the multiple of 8, right? Option D, you can see the option D, 32 is the multiples of 8 as well as this 40 is also multiples of 8, right? 8 into 5. Yeah. So the option is, the correct answer is option D, 32 kilohertz and 40 kilohertz. It should be always in the multiples of this bit rate, number of bits, right? So 32 kilohertz and 40 kilohertz. Just note on the solution. Here there is no calculation. There is no calculation. This is a 2-mark question. This is a 2-mark question, gate 2-mark question. It should be in the multiples of 8. That is what I given here, right? The same solution. The frequency should be transmitted. It should be the multiples of 8. So the option D is the solution. Then coming to the 9th question. let Q of root gamma be the bit error rate of a Bpsk system over an AWGN channel with two-sided noise power spectral density N0 by 2. The parameter gamma is a function of bit energy and noise power spectral density. A system with two independent and identical AWGN channels with noise power spectral density is N0 by 2 is shown in the figure. So the Bpsk demodulator received the sum of the output of both the channels, right? The question is, if the bit error rate of the system is Q of B into root gamma, then the value of B is, you are asked to find this B value. This is again very simple, right? So the question is bigger, but the answer is very, very simple. You are given with this diagram also. You can see the Bpsk modulator, the Bpsk modulation. Here you are going to give through two channel, right? AWGN channel 1 and channel 2. So the channel 1 output is, each one is going to have the bit error rate of Q gamma, Q into root gamma, right? Just see. I'll show you the solution, right? So the channel 1 output is going to have the Q gamma bit error. So Q of root gamma bit error. Similarly, channel 2 is also going to produce the same bit error rate Q into root gamma. So this is going to be added here. Then what will be the output? The output is going to have Q into root of 2 gamma, right? So that is, here Q is a function. It's a Q function. So I cannot add this Q, right? The function value can be added, right? So root of gamma plus gamma, it will be equal to 2 gamma. It is equal to 2 gamma. So the output is received signal is going to have Q into 2 gamma. But what is my question? The question is, you're asked to find what is the value of, if the transmitted signal is going to have B into root gamma, what will be the value of B in ketirukanga? Yeah, so this is what my question. You are asked to find the value of this B, right? Now, this is the output is actually Q into root 2 gamma. So I can write this as Q into root gamma into, root 2 into root gamma, Now, what is the value of B? You just compare. This is what the exact output, right? The output is going to have the sum of these two values, right? But it is given as Q into B root gamma. This is B root gamma, right? So you just compare these two values. You just compare these two expressions. So now what is the B value? So B is equal to square root of 2. That's all. B is equal to square root of 2. So no option is given. You need to find the solution, right? So this is very, very simple, right? They are given with two channels. Each channel is producing the bit error Q of root gamma. So the sum is going to be Q of 2 root gamma, right? I just write this as 2 root into root 2 into root gamma. So I can compare these two expressions. So B is equal to square root of 2. That's all. So I just comparing these two. So B is equal to square root of 2. Is it clear? All right, we'll move on to the last question. Yes. So move on to the last question. The message bit sequence to a DPSK modulator is 110011. The carrier phase during the reception of the first two message bits are 11 pi pi. Right? It is transmitted as pi pi. The carrier phase for the remaining 4 message bits. Totally are given with 6 message bits. For the first 2 bits, the output is received as pi comma pi. So you are asked to find the remaining 4 bits. So what will be the value for carrier phases transmitted for remaining 4 phases, right? So in DPSK, you can see the options, right? So we'll see the solution. So in DPSK, 0 is represented by 180 degree phase, pi, right? Pi radians, and 1 is represented by 0 phase. You can choose the reference bit. So before transmitting the Bpsk, you'll be using a reference bit, right? So the reference bit is 0, right? So here it is taken as 0. So for the demodulator, modulator output is, here the modulator output is calculated like this. This is going to be the reference bit. This is the reference bit. The reference bit is taken as 0. The reference bit is taken as 0. So this DPSK modulator is a simple exclusive OR operation, XOR operation. So you just 0 and 1, XOR the 0 and 1, the output is 0, and XOR the 0 and 0, the output is 0, then XOR the 0 and 1, 0 and 1, the output is 1. So if the two values are different, you will be getting as 1. If the two values are same, the output of XOR is going to be 0. So the DPSK modulator is simple XOR, exclusive OR operation, XOR operation. It's a simple XOR operation, right? So the output will be 0, 0, 0. So this is the input bit 1, 0, 1, 0. The total remaining bits are 1, 0, 1, 0, right? So the output is 0, 0, 1, 0, 0, 0. So first 2-bit transmitted is pi pi. It's given in the problem itself. Receiving pi pi for the first 2 bits. For the remaining bits, it is going to be 0 pi and 0 pi. Just put this 0, instead of 0, the pi is transmitted. Instead of 1, 0 phase is transmitted, right? So the remaining remaining received phases are 0, pi, pi, pi. So this is what the solution. This is the solution. Sorry. So the solution is 0, pi, pi. So option C is the answer for the last question. So option D. Option D, sorry, option C. 0, pi, pi. This is option C. I think I have just covered some of the things, right? Thank you so much. Thank you so much, students. Thank you.
Thank you, ma'am.
Thank you.